Hi everyone, this is Siddharth. I'm a security consultant at Redfox Security, and Redfox Security is essentially a solution provider and we provide a lot of services across a lot of domains for application security, infrastructure security, cloud security, adversary simulations, OSINT engagements, and so much more. So do check out our page and see if something interests you. Moreover, we also have an academy where we have a plethora of courses ranging from web hacking to Windows red teaming, infrastructure security, moving into iOS pen testing, AppSec, Linux privilege escalation, and I leave exploring the rest of these courses to you guys. And we'll quickly move on to the topic of discussion for this live, which is going against WannaCry Ransomware once again. So I have done a live stream on tackling WannaCry once before, but the last stream ended with me finding out that the actual WannaCry.exe is a wrapper and there is another binary inside of it. So what we'll do today is we'll try and understand what that embedded binary was doing. So yeah. X32 debugger. I used this last time to split open WannaCry.exe, and I'm going to go do that again. Right. So in the last session, I had noted a virtual address, which actually I'll show it again on Cutter in case somebody is new here. So dark theme, obviously. Right. Okay. So the main function here in a graph, right? So this is basically the main function of WannaCry, and as a quick recap, this was the URL on which it was reaching out to, and if it could not find something hosted on this URL, then the ransomware was not executing, it was not detonating rather, and this is basically the inbuilt kill switch for the same. Moreover, we had a lot of different functions here, and let me try and quickly spot the one which was actually creating. Okay, yeah. So this function, after creating services, after setting up a persistence for itself, this particular address, this virtual address, is from where the whole dumping the executable kicks off from. So let's go to the same address now. Okay, what is the agenda here? The agenda is to get that exe out and do an analysis on that embedded binary and not the wrapper itself. Now that binary is embedded in WannaCry.exe along with a lot of other things, a lot of other code. So getting it out is going to be a task which involves not getting my system be affected by ransomware, right? Because if I get it out and the system is affected by ransomware, then I cannot actually use my tools and everything so freely, because now everything has been botched. So what I am going to try to do is get this executable out without executing other parts of WannaCry.exe. One way of doing that, which works in case of WannaCry, may or may not work in all the cases, is finding out what function is being executed while like what function executes and creates that binary. So last time we had we were going through each and every function using x32 debugger, and this function was the one on whose execution we could spot the binary being spawned in C, Windows, and tasks ch.exe, right, that directory. So what I am going to do is I'll go to this expression, which is 407 CE. Oh. Okay. Yeah. Okay. And I'll basically make the EIP. I'll modify the EIP to go to that particular virtual address. Right. So now when I trace or step over the previous parts of WannaCry.exe, which would have normally be executed before reaching to this part, have been skipped, right? So now directly this part, like this sequence of assembly language, this assembly instructions will get executed, right? So I think it's quite a way down where it actually writes the file, but we'll just keep a lookout. Now this is because I know where this exe is going to spawn. It's going to spawn in Windows folder, and the name is going to be tasks ch.exe, so I know where to keep a lookout for. But in case somebody does not, then they can refer to the previous live stream on WannaCry Ransomware, and you can see that how we find out the indicator which leads us to this particular directory. And I think it would definitely be visible here as well. So from this, basically we are going to follow this graph down, right? Get to so we'll create a file, we'll write some data into the file and close that handle. In the process, we do get a handle to the kernel 32 DLL module, and it does there is a mention of create process, but it does not really get called as far as I know. And moreover, even if it does, we can skip it, because we have the power to modify the EIP. So we'll just skip it if that is what's going to happen. Nonetheless, let's start stepping over some instructions. So we get a module handle, get process address, and it's going to create. Okay, so now this is just a move command. It's not really executing this Win32 API. Find resource, load resource. Okay. Right. So now, as we reach this particular syscall, this particular Win32 API call, we do a move file exa, right? So let's look up what move file exa does, right? It moves an existing file or directory with various move options. Okay, so the first argument is the existing file name, which in this case is tasks ch.exe. Move it to the new file name, which is this particular file. Now there is no file as tasks ch.exe in this folder, so effectively this call is going to fail. And a very interesting part of playing around with malware and looking at all this is that the error handling has been done so well inherently in these systems that once you see a call, there will be this last error. This will get populated with whatever error there was. Error file not found, right? And this basically means that the existing file name that we had given to the Win32 API call was not found, right? what the malware does after that is something that we'll see. So okay, now we have create file A. Create file A is again another Win32 API call, which creates a file or an IO device. So this will essentially create a handle, right? So we open a file, and the first argument is the file name. So the file name is C Windows task ch.exe, and it's not here yet, right? So let's see a side by side of, do we see a file popping up here as soon as I let that call get executed. Okay, Win32 API call gets executed, and there we see it. A task ch.exe has spawned. Now it does not have any data inside of it. It is an empty file, because this is only creating a file, not populating it. The next Win32 API call that is going to populate it is called write file, right? So let's move ahead and get to write file. Now, what is write file, and how does that work in a standard call format, right? Write file. Okay, just write file. Okay. So here we give it a handle to the file that we created with create file over here. The second argument is the buffer, the actual data that is going to go inside of that file. The third is the number of bytes that are written to the file. Okay, and the other are optional. Moreover, they are out specifying arguments. Like, we don't really care much for these. So yeah, and as you can see that the first one is ESI. Okay, and this is definitely a handle, right? This hex value is a handle. Then is EAX, which will be the buffer which is going to go inside of the file. We can spot that buffer by, like, this is the address from where the buffer starts. We can go and follow this in the dump. So here you see the actual raw bytes of what data is going to go inside of task ch.exe. Moreover, what is going to happen here is you can see that it's starting with the magic bytes MZ, which is a telltale that this is a portable executable, right? So now we know that this is going to write a portable executable, and we know exactly where the data is. Okay, data is starting from. To know how much the data actually is, like what is the size of the data that is going to be put inside of this particular exe, is the third argument, which is number of bytes to write. So the third argument here is from EBP. Okay, right. Now what I'm going to do is convert this hex value into decimal, so that it's understood a little easier, right? So this is the hex value from the EBP, and this is the decimal value. So basically, these many bytes, that is the amount of data starting from this virtual address. That is a chunk of data which has the actual the actual executable that we want to extract, find out, right? So we have two ways of getting this data out. One is the very simple way, that we let it run, okay, which I'll show you. Let's let this run. Let's let this is called run. Okay, so write file done, close handle done, and task ch.exe has been populated. Why I find this method quite risky is because now a lot of code not related to the actual executable, like not just the write file part, has been covered by me, right? I have let it execute. I could have started, like I could have put the EIP and let it start from here as well, right? But for right, so that is one way. I could have done that as well. But in cases where that is not possible, right? Maybe there are a few calls which are being executed between this create file A and write file that you do not want to execute, right, on your system. In that case, you can do something different. So right now, if I execute this, I'll totally annihilate my system. This is basically what WannaCry ransomware actually is. This has the encryptor. This has basically everything. So as you can see, we can like there are new icons popping up on the desktop, and we'll probably see things getting encrypted, right? So things have started getting encrypted. The old files have not been deleted yet, so like it's in process, definitely. And the much awaited wallpaper is now here, right? So as you can see, like I can just close the x64 debugger now. So the rest of the wrapper does not run, but that is one risky way of extracting the binary. So I'll show you another way which requires a bit of math and using hex editors to calculate the relative virtual address and the offset. So I'll shut this down for now and reset the environment to the part when I had not actually executed the malicious binary. Okay, so till then let's look at the comments. Okay, Dhruv asked which malware sample was the hardest you've ever worked on. It's definitely WannaCry for me, because WannaCry has a multi-tiered portable executable thingy, where like you'll see further, where the original wrapper creates a service and an executable, and then this new executable that has been created, this, when I run it, it creates a new service and some new executables as well, and all of these things work in tandem. So it's very difficult to keep track of what exactly is being done by which binary, because a lot of things overlap, right? So I would say it's definitely WannaCry, but it's really fun to go through the assembly instructions and see the whole graphs of how code execution actually works. If this was written maybe in NIM or Go, or this was compiled with Clang, then it would have been a very big issue. But luckily this has not been compiled with Clang, so working on this is relatively easy and relatively easier to understand as well. Okay, let's see what the other method is. So again, we'll go to the X32 debugger. Anybody who's wondering why this is X32 debugger and why not X64 debugger, because the malware authors They are very considerate. They want their malwares to work on all systems, which are 32-bit or 64-bit, all of them. So they write their malware in 32-bit, and hence. So yes, we will have to. I forgot the actual address. We'll probably have to go through that again. Okay, so this is a tool called CFF Explorer. It is used to get a vibe of the portable executable. This has a utility called address converter, right? So what I am going to do here is I'm going to find where that like I did a follow and dump. So I'm going to find where that actually resides within the executable. Okay, so let's go to, what was that, 407C0. This is that. Yeah, let's move to, okay, I think we would have to execute this at least for now on a breakpoint. Okay, there's the EIP. Let's let it run through. I think there's a few jump instructions which I did not pay attention to, which transports the EIP to somewhere else, because I can't see the right file. Oh no, here it is. Never mind. Okay, so the EAX, let's follow this in the dump. Right, so the address here is 710.0A4. Let's add this here, 710.0A4. And now, basically this has calculated what the file offset will be for WannaCry.exe if I want to find that exact address, which is going to be 320A4. And as you can see, this is again starting with MZ, so definitely it's an executable. Now I know how big this binary is going to be due to this EBP over here. So I have EBP, which is telling me how big this is, and I have this particular offset which is telling me where it's starting from. So we can use a utility called DD. It's essentially inherently a Linux utility, but we can use it within Windows environments as well. Okay, so what we're gonna do is we have this is signifying that we're dealing with bytes. We are going to skip how many bytes? Yeah, so for that we need to convert this number into decimal. Okay, so 32084. We need to skip these many bytes. 204964, and this is the number of this will be the number of bytes that we actually do want to read, which will be 3583. This number 3514. Okay, right? The in file will be WannaCry.exe, and the out file will be tasks. Rather, let's just call it output.exe. Now you can do this in a fresh snapshot as well, so that the previous instructions have not been executed. For demonstration purposes, I'll run it right now, just as is. So okay, nothing on the desktop called output.exe, but there is a WannaCry.exe. Okay, so this created a file called output.exe, right? It read exactly 3514368 bytes starting from this offset, and after that is whatever data it read, it put into a file called output.exe. So essentially exactly what the malware was doing, but just to skip that ambiguity or ambiguous portion, we have got output.txt over here. And just as a proof of concept that this is actually functioning, this is actually like properly functioning as malware, as soon as I execute it, we can see a lot of things pop up. Again, a few more exes, the WannaCry decryptor, and I think we will see that infamous background soon as well. There you go, right on cue. Everything will start to get encrypted. Definitely not, but doesn't matter because things are getting encrypted. It's not able to delete the old files yet. I think it's still working on that, but we can see things getting encrypted instantly. Okay, so now we'll start doing an analysis on the actual tasks ch.exe. And while this restores, let's okay, so Shashi asks, how can I start my journey in malware analysis? I think the best way to get into malware analysis is picking up malware samples from, I think there are a few repositories that you can find online where there are people who do malware analysis on a particular binary, and then they basically let you know, like give you a report on how they did it. So for me, that was a very nice way to do that. Another thing, Flare VM is something that you can install or set up in your home lab, where you can have a safe environment to detonate all your malware, and that is a good way to start, because then you get more hands-on practice using the tools and not just theory. For example, this tool DD, if you just read about it and not actually do something with it, then you might actually forget what DD is used for, stuff like that. So I think picking up malware samples from repositories is a great way. Okay, so now this is a snapshot where I have already extracted the tasks ch.exe, and we'll work on this. So as always, we will use PE Studio, which is an amazing utility. This takes a while and a lot of resources. Okay, yeah, you can see the computer getting a bit slow due to PE Studio hogging the resources, but that tells you that it really does a great job. Again, this tool lists out the capabilities of the executable based on the indicators that it finds in the imports, in the libraries being used, in the strings that it finds, and hence this can be used to triage malware or understand its behavior better. Actually, PE Studio does the same, but PE Studio is much more robust in these areas. So first, as a sanity check, let's look up the SHA-256 hash of this binary and see if it has any old hits, right? It definitely should, because that's WannaCry, right? But let's just see. VirusTotal. Okay. Okay, let's do that after PE Studio is done hogging all the resources. But from a kill chain perspective, this binary can do defense evasion, can do discovery, execution, persistence, and we can see that it probably interacts with system services. It creates processes. That's what it's doing. And definitely it's trying to encrypt data. That's what WannaCry is all about. It definitely has an encryption key. Defense evasion, obfuscation, code discovery. Okay, definitely. File system copy files. As you saw that when I executed it, there were a lot of new files being created. So it definitely is copying files from within itself to the file system, creating directories, get file attributes, interacting with the registry, creating and terminating processes. More capabilities include hash data with CRC32, encode data using XOR, encrypt data using AES, and is referencing AES constants. Okay, so all this information that I am extracting using this particular tool will help us triage the malware and understand its behavior. So now, because I see all these things before I step into something like decompiling the malware, I'll actually be on the lookout for where is XOR being used, where I'm seeing some function which is probably doing something to encrypt some data with AES, or where it is interacting with the registry, where it's writing files, stuff like that. So the objective of this is to be able to do that. Moreover, it's checking if file exists, get the host name, create process on Windows, terminate said process, persist via Windows service. Now, this is something that all the binaries from WannaCry, I think, were doing. The original wrapper was also persisting using a Windows service, and so does this one. So that does line up pretty well. Let's see if I can successfully copy the hash this time. Wait, I can just click to follow the link. That would have been much easier. Yeah. Now this is a sandbox, so internet is not accessible here, but outside the sandbox, okay, so a lot of vendors are flagging this particular hash or any file with this hash as malicious. 67 out of 72, that is a very heavy score, and a community score of minus 2900. Now we can find the whole triage using just VirusTotal, because it has a lot of details about the binary whenever it actually ran the executable. As can be seen here, the last analysis was done just 3 hours ago. I think it was done by me only. We can obviously put it up for reanalysis, and it lists out what IOCs can be found, and it lists out everything very well. And this is a very interesting and a very nice source of triage for well-known malware. But if this malware was not well known, then some analyst might have to do this manually the way we are, and a lot of behavior can be mapped out by these sandboxes. But initially the analysis was done manually for WannaCry, and the kill chain found by Marcus Hutchins was done manually as well. The kill switch, my bad. Okay, so we have some indicators over here, and the first indicator is the imports, which has a very high level. Okay, let's go to imports and see what it is flagging. Create service A, registry set value, virtual alloc, virtual protect, write file, create process, terminate process, crypt release context, ran, sran, set current directory. Okay, we can see why these calls have been flagged, because they are associated with TTPs, most likely out of the attack kill chain. And you can also see what library this is from. Now, if you remember, if you have seen the previous live stream, you would know that the actual libraries in the previous in the wrapper binary did not have kernel 32.dll, user 32.dll, or any of these. However, in the strings section, which we'll get to, these names were mentioned. So this was because those names were in this particular embedded binary and not the actual wrapper, right? So hence, now when we are doing an analysis on this binary, we are seeing all of those not as just strings but also as libraries. Okay, so the flagged strings have create service. Okay, these are basically the Win32 API calls, right? We have a DOS stub over here, and we have stuff like command cmd.exe/c and a C descriptor, a C format string basically. So this, I would assume, is being used with printf, or an initial string is being created with sprintf, right? Task ch.exe, obviously, yeah. Okay, that's the file name. And then we have things that look like commands that you would execute in cmd.exe, which makes sense because there must be a function inside of it which executes it, right? So we see some shady stuff over here, which we'll get into, right? Either way, this is pretty much it for the static analysis. Let's dive into the dynamic analysis. One thing, there is a PK, there is like a PK zip self-extracting archive in one section of the binary, right? Okay, so the last time these three sections were okay, but there was one weird section which we had flagged, and it's the same here again, because this essentially has all of those files inside of it. As you can see, it's 98.14% of the whole binary, right? It has all of those files and executables inside of it, which will come out, and which will spread across my desktop when I execute it. This is pretty much it for the static analysis. We'll do the advanced static analysis and advanced dynamic analysis together. Before that, let's detonate it again, but this time we'll keep a watch on what exactly this is doing, right? Process name is ask ch.exe. Apply. Okay. Okay, let's capture, and this will probably make a lot of noise. It should. Yeah. Let's let that run until we get that infamous background, because then we'll see exactly what all this binary was doing according to procmon. Okay, I think this is pretty much it. Yeah, so we see a lot of activity. Nope. We see a lot of activity by this process, and towards the end of it, it's basically listing out or accessing each and every single file on my disk, right? As you can see, right? Like to pick an example, yeah, so I think this whole directory has been parsed by the malware. And then it's writing files. So initially it read, and then it's writing the file after encrypting it with AES 256. Reading all the files. Yeah, okay. Let's see if it also actually does some TCP operations, because the original binary was doing, right? Contains TCP. Okay, so not really. No TCP operations. If this is executed, then the malware will definitely detonate. Only the wrapper has the kill switch. This binary does not. Okay, cool. So this executed pretty well. Let's see the process tree, what all it executed under it. Okay. So it used the attrib.exe, the icackles, taskdl.exe, which it created on the desktop back there. WannaCry decryptor @.exe, cmd.exe, within which WannaCry decryptor taskdl.exe. Okay, so that is, I think, a recurrent thing, probably being done on a routine in a loop, right? So that is the processes that are being spawned by this task ch.exe. Let's revert this and get into a little more advanced static and dynamic analysis and see interesting things happening. Okay. All right. Okay, not this. Yeah. Okay, so this is the graph for main, right? So initially it has a pretty linear execution from the looks of it, but with how many functions there are here, this is definitely a lot more convoluted than what is visible, right? So we can go through and look at these functions, see what they're doing. This one does a get computer name W. Okay. So it's basically running the hostname.exe without running the hostname.exe. Then we have this particular function. This looks more interesting. Okay, it has a lot more inbuilt functions. We can go through each and every one of these functions and try to understand what it's actually doing, but this is so convoluted of a code that would prove to be difficult. But still, this does not defeat the purpose of only doing dynamic analysis, because there are a lot of things that we can figure out from just the code, right? Yeah. Okay, we're copying some files. This I think is the exact same thing that the wrapper was doing. Okay, this function right here looks interesting. Okay, so we have some Win32 API calls here. Opening SC Manager A, if you recall, SC Manager A. This basically creates a service, opens a service control manager, and the output is an SC handle, which is passed on to other API calls, open service A, start service, stuff like that, right? So it basically is creating a service, rather starting a service, and if it does not exist, it's creating a service. Now, I have not written this code. I can only deduce, right? And I am no assembly maestro that can, who can read all this code and understand all of it. But what I can see from here is we're opening a handle to a service. If we can open it, then we start it. If we cannot open a handle, that means the service is not there. Hence, we create it and then start it, right? And then we close the service handle. So this particular function is just to execute a service, whatever service it may be. If we go into dynamic analysis, we'll probably be able to understand what service it is by looking at the ESI this LP service name during dynamic analysis. Okay, so that was that. Then we have this function which is creating a process waiting for the output, then terminating the process, then closes the handle. Okay, so essentially it takes this function takes input as some command line and then passes it on to create process A. So essentially what this function is doing is it takes whatever is behind it, like above it, as input, so EAX. So during dynamic analysis, if you look at whatever there is in EAX, that is the command line argument that is going to be executed by this process, which from the strings can be deduced as attrib.exe or iCackles, right? Okay, go back in main. Okay. c.wnry was a file that was created on the desktop and I executed it. So I am assuming that what this function is going to do is create those files. And okay, so now here is the live example, right? We have attrib, this is potentially plus h and then a period, and it's passed on to this particular function which was taking the command line in. So it will essentially execute attrib plus h dot. Now plus does not get printed in the assembly note in the way that assembly is written here, but that is what I deduce this to be, because what that will do is it will hide the directory that the malware is in. Moreover, iCackles grant everyone full access is what it seems to everything, and again that is pushed into this function as well. So that deduction is most likely correct. Now a lot of these functions will be dead ends. That's just how it is. But for proper analysis, it's important that this is done. And a lot of it is based on intuition, which may help you out sometime and which may hold you back. So it goes both ways. And okay, so now it's gonna probably create the t.wnry, and that seems to be the trend. Okay, I couldn't find a function which was interacting with the registry, but let's try to do that using the debugger. Okay. Now to do that, okay. I'll actually have to open Cutter. Okay, so the breakpoint has to be again in the main. Okay, now we can go one by one through all the assembly instructions. Get module name is, oh no, that is unfortunate. I accidentally click on the run button, and I'll probably have to reset this because that. In these cases, it's very important to have a snapshot where you can go back to like a clean environment where you can test. You don't want that detonated wallpaper haunting you in the background of the pop-up. Okay, so get module file name is basically it's gonna call a Win32 API, which is going to tell it what process or what is the actual location where it is residing. So I think you can already see it populating through the calls. Okay, so it's going to set the current directory to wherever the actual malware is, and then it's going to execute some stuff. Okay, so for better visibility of what is actually happening, let's keep the desktop visible. We don't really need that. Yeah. So we found a lot of functions which were doing some of the other stuff. We can keep a lookout for them, and then we know what to expect. Why is this not? Yeah, so I think we are this has passed. Okay, we're probably somewhere here. Okay. Now currently, if I go to the users analyst, now the desktop has a bright icon. That means it's not hidden, right? So let's see if that changes, because here where we currently are, I think we're on somewhere where we have just executed set current directory. We are soon going to have this function to be called, which will change the attribute to hidden. So let's see if that happens. Now that will most likely happen because that's how the malware is written. But that solidifies the behavior that we had guessed. So here that particular function is being called with this command line. And as you saw, the icon went from bright to dull. So it essentially, now this is a hidden folder. If I do not want to view hidden items, desktop will be gone. Now the original idea was not to hide the desktop, but whatever folder the malware is in. Then it does an iCackles and grants everybody the authority to execute this, because again, malware writers are very considerate. They want everybody to execute their malware properly. Okay, now we're getting into function calls, which will create lots of files. Now this is probably the routine where it's going to create those extra files. Okay, so those extra files I think were created a little way back here, right? Yeah, so right before, I think I forgot to mention, but right before it hit the desktop, it created all these new files on the desktop itself. Then it hid it, granted everybody access to these files. 70A. This will probably this seems to be something that's doing a lot of action with files. So let's see what it actually does. Does it do anything? Does it not? Okay, so now these files have been populated with data inside of them. We can go and read this stuff, but I don't think it will make sense. Okay, so this file does make sense. This particular file does not. Let's keep going on. The idea is to find the call which eventually triggers things, right? So does this trigger something? No. Does this trigger something? Now, definitely, a lot of actions that are being performed by these calls can be seen as host or network indicators. You can set a procmon to list out all the registry actions, and that way you can see it create this particular key, right? It creates the environmental variable for where the malware resides. This is not a default registry key. So basically you have to go through these calls. If you don't understand the code like me, then you go through these calls, see where something malicious happens. Because for example, I think this call EAX will actually trigger everything. So if you want to know what's happening, then you have to investigate what EAX does, right? Because if you're calling EAX, and this is what we can see if you go into the dump, it's not a executable, it's not a portable executable. So this if we call some arbitrary place, it's gonna run a function. Now let's actually copy this value and try to find this in Cutter. No function detected, cannot display graph. I think this might need some conversion, as I was saying, but the idea is that whatever lies in EAX over here, is what we want to investigate next, because as soon as I do a call EAX, now the debugger stops, it has loaded DLLs, it's running, it's not in a stop state, and you just see things happening. So this particular location in the memory, it has some sort of either shell code or instructions or a function, which is doing all this. Now I don't know what that is, right? I'll leave that for part 3 of WannaCry dissection. If you're interested, do leave a comment, and till then, if you're really interested in understanding what actually resides on this particular address, this particular virtual address, which is causing execution, which is causing so many new files to be created automatically while it's not a function itself, right? Then you can look at shellcode scalping or memory scalping and try to fish this particular payload out, or convert that address and try to find it in Cutter if that at all is possible. And that is something that I am going to try if you guys really want a part 3 for this. So do leave a comment. And that's it for today's live stream session. I hope this was fun.